Hello, everyone. Um, we will be discussing um, about the universe, the how universe began, and what could be the possible ultimate fate of the universe. So, the title of this video is Big Bang and the Fate of Universe. So, let's just begin. So, um, I will be briefly talking about the debates on the universe that's always happening in this universe, and from there we move on to the possible explanations of how this universe came into being, and mainly the Big Bang theory, and we will also look for the evidence why we believe that the Big Bang is the right theory, and what kind of structure universe has as of now, and what could be the possible end of the universe. So let's just begin. So um, there has been a lot of debate on the universe since the beginning, because probably the stars were the very first thing that the human noticed on the sky. So stars have always been mysterious to humans, and humans have been using stars all along for thousands of years. So, but let me tell you that everything in this universe is controversial. The universe itself is very controversial because we are always debating about almost every aspect, and these debates are sometimes academic in the context of science, and sometimes philosophical. So, for example, so let's just begin with this question: that why there is a universe anyway? So this is I think this is more like an ethical question. So it does not really fall into the realm of science. So the science can explain to you probably how the universe works or something, but it cannot give you the answer that why there is a universe in the first place. So 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 okay, for the whatever reason we have a universe. So then the next questions are how this universe begin, how does it work, and how will it end. So these are three big questions, and all of these fall into the realm of natural philosophy. Well, that's science. So I think these are important from the science perspective. So before we start, we move on to discuss the beginning and ending. Let's just for now understand how the universe works and what kind of debates has been there. So we started from the early Greek school, that try to everything in this universe in terms of four elements, and those four elements were fire, water, air, and earth. And then the Chinese came along the way, and they said, no, okay, let's make it five. So they have wood, fire, earth, metal, water. So everything that's happening in this universe is just interaction between these elements. So for example, here on you see two pictures. On the top you have this Greek model and the symbols, which shows the fire, water, air, and earth. And then in the lower figure, you see the Chinese model, and these arrows just explain the interactions between these elements. So everything in the universe can be explain in terms of elements and their interactions between them. But now we have 118 elements. So the ancient schools has been, let's say, have been made more specific, or let's say in a way more detailed version. So now we know that there are 118 elements, and probably about 100 elements are nearly very stable, and the interactions between these elements are driven by four forces in the nature. So what are those four forces in the nature? The gravitational force, the electromagnetic force, the strong force, the weak force. So let's just briefly describe them for those who are not familiar. So the gravitational force means that there is a force of attraction between any two mass objects in this universe. Those mass objects can be very tiny particles, or they can be the very big galaxies, but there is always a force. And then there is electromagnetic force that deals with the currents and the magnets. So you know that when there are two charged particles, okay, let's say one is a positive charge and one is the negative charge, so they will just attract each other. And the like charges, or let's say the positive and positive, they will just repel each other. They will move away from each other. So this and then you also know the magnets also have an effect on the metals, also on the charged particles. So these come in the electromagnetic forces. And then we have strong force and weak force. These forces are basically inside the nucleus of an atom. So you know that everything is made of atoms, and atom has a nucleus in the center which has protons and neutrons. Now there is a big question. Okay, neutron has no charge, right? But the proton has the positive charge. So the positive should repel. They should not be living in a very tight space in the nucleus. So how do they live? So there should be some force that is attractive. So that's called the strong force. And there is also a weak force also that is also a part of a nuclear force. So now together we call strong force and weak force nuclear forces. So for our most part of the science, I think, or engineering, let's say, first two forces are enough. Let's say the gravitational force and electromagnetic force. If you know them very well, you can probably explain most of the phenomena in this world. Okay, that's a bit controversial, but let's just agree. So okay, one thing that on the large scale, the gravity dominates over other forces, mean that no other forces play roles when we are talking about the scales of a galaxies or a group of galaxies or even stars. Other forces do not seem to play significant roles overall. So that was how universe works. So as we started that about the debate, so the question is that starting from our early understandings of the universe, how did we arrive where we are today? So the ancient beliefs was that the universe is created from nothing, and the second is the universe is static, and the third is that the stars are basically holes in the sky through which the lights of the heavens reach the earth. That was a very ancient view. I love that actually. So yeah, the universe was created from nothing, and the universe was static. Static means that the galaxies and stars, they are not moving. And these early beliefs, or let's say observations, they just led to the first model of the universe, which is called the geocentric universe. So in the geocentric model of the universe, we believe that the earth is actually everything in this universe is static. So is the earth, and the heavens itself rotate. So let's just I give you some examples. So the stars and galaxies are just like embedded in the space around the earth, and when the sky itself rotates, so those embedded stars, they also rotate around the earth. So that was the early view that was put forward mainly by the Greek scholars like Aristotle or Ptolemy. And then latest in the Renaissance, when in the European Revolution, this it was actually observed that if you assume that the earth is static and the sky is rotating, and because the stars are embedded in the sky, so they appear to be rotating. If this is how you explain the universe, then there are many observations that cannot be explained. And then in order to account for that, so we realized that the sun is actually the center of our solar system, and all the planets around the sun, they are moving around the sun in the orbits. So here in these pictures I have shown you the models. So for example, this left one is the geocentric model. So you have a earth in the center, and everything else, all these, even the sun, moon, other Mars, planets, all other stars, they are embedded into the sky, and they rotate around the earth because the sky rotates. And here in the right figure, you see that the sun is in the center here, and the orbits, the planets, they orbit around the sun, and also the stars, they also seem to rotate around the earth. And later we found out that the earth is spinning basically. So it's not that the sky is rotating, it's that just that the earth is spinning around its own axis. That gives a false impression that the sky is rotating around us. So basically, and the current view is that the universe is dynamic. Means that everything in the universe is in motion. Universe is not static. So what does it mean? That although we say that that the sun is the center and the planets is revolving around the sun, so that does not mean sun itself is static. The whole solar system is actually moving with the sun when the sun moves in the Milky Way. So sun is just one of the stars, one of the billion, like hundreds of billion stars that we have in the Milky Way. So now we discussed a bit history, how we came from a static universe to the concept of dynamic universe. So when we study the universe, we study it in actually two ways. So one branch of science is astronomy. So astronomy is actually the branch of the philosophy that deals with the individual celestial bodies like stars and galaxies, their motion, the processes happening in them, how they form, how they die. So all of this we study in astronomy. So keep in mind, this is for individual objects. But how about the universe as a whole, as a bubble? So that we call the cosmology. So cosmology is the branch of philosophy that deals with the creation, evolution, and even ultimate fate of the universe as a whole. So when we talk about that the universe is a big bubble in which the galaxies and the stars, they make this bubble. So how this bubble will evolve, how it will burst, or if it will burst. So these kind of study of universe as a whole is cosmology. So let's just move to the Big Bang theory. Before I go to the Big Bang theory, so there were there are lots of speculations about how the universe came into being. Some people believe that universe should be a cyclic process, like universes are created and then they die and then they are created again, and this keeps going. That's obviously one possibility, but that does not rule out that this in current epoch, or let's say episode, how this episode began, that's actually the question. So Big Bang theory is one of the most popular, or let's say accepted theory in science, and I will explain why. So it started at 13.8 billion years ago. So our universe in which we live, that we see, the universe we see around us, is 13.8 billion years old. So in 13.8 billion years old, the universe was very tiny, hot, and dense. Something. So now what does this mean by something? I use the word something because you can't really see that it was a point. It was very dense, very small, very hot, but I cannot say it as a point, because if I say this is a point, then it means I am talking about the space. And when there is a space, there is time. But the space and time started after the Big Bang. So I cannot say that before the Big Bang, in the start, there was a point. So there was just something. In science, we just call it a singularity. But honestly, physically speaking, we don't really know what the word singularity really means. So what happened was that there was hot and tiny something, and then that something suddenly started to expand and stretching the space itself. So this ancient belief that universe came into being from nothing is a very scientific view, actually. And then the universe expanded, and we know that when the gases or the materials, they expand, they cool down adiabatically. So the universe, when this hot, there was no particles, no materials, no atoms, no molecules back then. So let's just call it some kind of a soup. So when that cosmic soup in the start, when it cooled down a little bit, then the particles started to form. Particles like electrons and quarks, and then when it cooled down a little bit, the quarks also merged into protons and neutrons, and then electrons, proton, neutrons, they merge together to form atoms. And initially it was hydrogen atoms, because the hydrogen is the smallest atom. And then these atoms, they started to fuse with each other, and they became heavier elements also, like helium or lithium. And I mean, not very high elements, but let's say initially high elements a bit, they were also made in this Big Bang process. Now I tell you one very strange thing, that these things, they happened in a very small fraction of time. I will show you in the next slide what's the time scale over which all of these processes happening. Okay, what happens after the fusion, or after when hydrogen atoms are formed? So when the particles become more massive, the gravity dominates other forces. This is a very simple rule. So when the gravity dominated other forces, the gas clouds, they started to collapse on themselves. So when something just collapse on themselves, it becomes hot and it starts to burn. We will discuss it in another time. And this leads to the stars. So the stars are basically the burning hydrogen gas in the clouds. And then these stars, they are also stars. You can consider them as particles. And then these stars also have the gravitational force which is attracting them. So they make a galaxy. Okay. So this is how the galaxies is formed. And then there is another, we have to use this theory to fit into the Big Bang. Otherwise, Big Bang doesn't make sense. That's called inflation. So inflation is a very small time. It happened at very small time, from 10 to the power minus 36 to 10 to the power minus 33 seconds after the Big Bang. So we believe that in this time range, the universe expanded enormously out of nowhere. We don't know how it expanded, but yeah, this has to be there if we want the Big Bang to work. So the current understanding is that the universe is expanding still after the Big Bang. After 13.8 billion years later, the universe is still expanding, and it does not seem to roll back. Okay, so here is this picture that very famous. It's called the bell curve. If you see, it looks like a bell. So here on the left side, you see that this is the Big Bang. So this is the time 0. So the Big Bang happened at the time 0, and then at 10 to the power minus 30 something second. So here you see these two arrows, these red color arrows. This is the inflation period. So this is the inflation period up to 10 to the power minus 30 second. So you can imagine how small a fraction of time is this, from 0 to the 10 to the power minus 30. It's a very small fraction of a second. It's very small time. So in this time, the universe expanded a lot, and because of the expansion, started cooling, and then the protons started to form, and then the nuclear fusion happened, and then the hydrogen and heavy elements start to form, and at some point here, about 380,000 years ago. So this neutral, actually, the universe became neutral. Actually, before this time, there were not atoms. It was only the nuclei. So when the nuclei then capture the electrons, it becomes a complete atom. So at this time here, so the electrons and the neutrons and the nuclei, they form atoms, and the universe becomes the conditions are perfectly right for having a start of the universe. So when this hydrogen gas, it started to form, and due to the turbulence and the motions of particles, so there were some clouds of gas all over the universe, and those clouds started to collapse on itself as they become more and more heavy. So, and then we started to form stars and galaxies. But there is one strange thing. I mean, from the start of the Big Bang till here, we are still expanding. If you see from the start, this bell is becoming larger and larger, and now we are here. So this bell is becoming larger. So means that we are expanding. The universe is a bubble, but this bubble is expanding. Consider this as an example of consider an example. So for example, suppose you have a balloon and you inflate that balloon and put 2 dots on the balloon with the marker before you inflate. So when you inflate, what you see? You see that as the balloon is inflating, the distance between those 2 points starts to increase. So this is an example of how the universe is expanding. So universe is kind of a bubble, and when the bubble expands, we see that the points are moving away from each other. So this is a nutshell of a Big Bang theory, how we started from Big Bang, going through certain processes. We formed particles, then formed atoms and nuclei, and then formed hydrogen clouds and stars, and those stars make the galaxies, and then the galaxies are moving away. So there is this question that what's the evidence? Why we believe this story? That's really a big question. So I think the observational evidence for a Big Bang is overwhelmingly strong. This is one reason why people stick to the Big Bang theory. So there are some fundamental evidences. So first is the Hubble's law. So Hubble's laws actually tells you that the galaxies are moving far away from each other as the universe is expanding. And how do we know this? By measuring the redshift. So what do we mean by the redshift? Actually, the galaxy has a spectrum, and okay, I give you an example. So let's suppose we have a white light. It's coming from a star. Now, if this star is moving away from you, this white color will become red. That's why it's called redshift. But there is an opposite of it. It's called a blue shift. That if the star or galaxy is moving towards you, that white light turns blue. So, well, that's very strange that light change the color just because of the expansion of the universe. So we are in this first case. So this is more appropriate for us, that the stars are moving away from stars, or the galaxies are moving away from us, and the white light gets red. So because we know that the light, when it was emitted, it was white, and when it reached us, it became red. So from there we find that, okay, this star or galaxy is moving away from us. There is another phenomena. The farther you go in the universe, the higher those galaxies are receding away from you. So what does this mean? That the nearby universe is slowly expanding, and the faraway universe from us in the Milky Way, the faraway universe from us is expanding even faster. So these two evidences, the universal expansion is the first clue that the Big Bang happened, because the Big Bang is all about expansion, right? So the second evidence is the microwave, the cosmic microwave background, CMB radiation. So what is this? So everywhere we see in the space there is a microwave radiation coming from all possible directions. Now this radiation, according to the Big Bang model, should be present in the universe. Why? Because at the time in the Big Bang, when the nuclei of atoms, they captured the electrons to make full atoms, at that time the universe released a light. So, and that light, it was a flash of light that expanded in all direction. And because the universe is expanding, so that get red shifted and now it's not very high energy, it's in the microwave radiation. So the microwave radiation is not very high energy radiation like X-rays or the gamma rays, it's very low energy. So this is the second evidence. And what's the third evidence? That the galaxies look different. So the galaxies which are close to the Milky Way look different from the galaxies that are far away from the Milky Way. So now, okay, that also tells you that the universe is expanding. So you should ask me a question that when the Big Bang happened, the gas clouds formed. So the stars and galaxies, they started to start at almost the same time. So why the galaxies look different? Yeah, that's exactly the reason. So actually, when we are looking far from the Milky Way or far from us, we are looking back in time. I give you an example. So the sun you are seeing at this time now is 8 minutes ago. So it just means that if the sun simply or disappears, you will know this after 8 minutes, right? That the sun is gone. So the sun we see is as now is actually the 8 minutes old. 8 minutes ago it was. It's because the speed of light has a limit. Although speed of light is the fastest thing in the universe, is the fastest speed, but it's still very limited, because when the distance is very large, even if something moves with the speed of light, it will still take a lot of time. So that's why light takes 8 minutes from sun to reach the earth. So that's why when this the current light we see now, it was emitted from the sun 8 minutes ago. So having this argument, so when we see the distant galaxies, we are basically seeing back in time. So even if the galaxies were formed in the same time in the universe, when we observe them with the telescope at very large or distances, we actually, in the real time, we see that those galaxies are still very young, because we are seeing back in time. And then there is another explanation and evidence of a Big Bang. That's in a proportion of observed proportion of hydrogen and helium. So the Big Bang really tells you how much hydrogen and helium should be produced, calculating from how much galaxies we have, and we can measure how much how much helium and hydrogen in these stars and galaxies are, and then you can compare it with the predictions of Big Bang, and they seem very closely matched to the predictions, ridiculously close to the predictions of the Big Bang. So it means that the hydrogen and helium are very they do not decay very easily. So it means that the early universe, few minutes old, we still today have as much as helium and hydrogen that was there back then. So so all these evidences tell you that the universe happened from a big bang. Okay, so I told you the cosmic ray microwave background radiation, right? CMB. So this is the CMB map. So you see this green color and the red color is evenly scattered. So this is the whole map of the universe. So this green color, this red dot, so this is the actually the color map of the radiation. So it's almost coming from all directions. Yeah, there are some anisotropy, but it's quite homogeneous overall. And then I told you that the galaxies look different. So these are two very big evidences of the Big Bang. So in the right figure, you see that we call it the Hubble sequence or the galaxy sequence. So the galaxies, they can be either, so you see two branches, right? So one is this pink color and one you see the yellow. So the yellow galaxy, they are called the bar in the galaxies. They have a bar in the center. Okay, the galaxy has a bulge in the center, and then it has a bar, and then it has the spiral arms. So you have this bar in the galaxies, and then you have this simple galaxies which do not seem to have bars. They only have the spiral arms. They only have the spirals. And then there are galaxies in which they are just like elliptical. They just look like an ellipse. They don't seem to have bars and spirals. So these different galaxies show the different age and many other processes, of course. So this is one evidence of Big Bang also. So how these current and universe look like? So trust me, when we are talking about the universe as a whole, we are talking about the largest scale possible that we can only probably we can only calculate, but we cannot imagine. So stars, okay, so the universe actually forms like a web of clusters, and those clusters are made with galaxies and stars. Okay, I explain. So the stars form from the gravitational collapse of the gas clouds. This is the first stage, how this web is formed. In the second stage, the stars make galaxies, right? So a typical galaxy has about 2 billion stars. Galaxies then form a group of galaxies. It's called the cluster of galaxies. And then galaxies even merge. So the stars also form the clusters, and then the galaxy, and then these clusters form the galaxies, and then the galaxies form the from the clusters called galaxy structure clusters, and then those galaxy clusters form together and make super clusters, and then this web of super clusters is called the cosmic web. So here in this bottom picture, you see the how the cosmic web looks like. You also see some void, right, inside the, so it's like a spider web. And by the way, our Milky Way universe, that lives in Laniakea supercluster. So Laniakea is the local super cluster in which Milky Way is at this arm. So you see this red dot here, right, in this picture on the top. So this red dot is the Milky Way here. So the question is how this cosmic web will evolve in time. Will it just collapse, or will it expand? what's gonna happen. So this will tell you the fate of the universe, and that's exactly what we want to ask now. So the end of universe is it depends on so many factors how the universe will end. So generally there are two speculations. So one is called the big crunch, and one is called the big rip. I'll explain the reason. So you know that the universe is expanding, right? But at the same time the gravity is also attracting the universe. But because the universe is expanding currently, so we say that the repulsion is higher than the attraction. Now, if somehow in and that is that okay, so the attraction is due to the force of the gravity between the galaxies or structures or the clusters. But why it is expanding? So how do you explain this repulsion? So this repulsion has to be explained by the dark energy. We don't know what it is. But if the universe is expanding, when we say the universe, it means the space itself is an expanding, and everything, and because the universe is in this space itself, so the universe is expanding. And so this expansion, galaxies are moving away from each other. This repulsion should have some kind of precursor or a reason, and that reason is the dark energy. So the dark energy makes the universe expand. So now there are two possible scenarios. So if over time the gravity wins, I mean the attraction wins the repulsion, that will be the big crunch. So for example, there is this figure in the bottom, and you see that okay, from the left side we started from the Big Bang, and then we started in the expansion of the universe, and we keep expanding, and now we are here. So what are possibilities? So one possibility is that the gravity wins. If the gravity wins, we start to contract again, and we end up here again, a kind of a bang. So that will not called Big Bang, it's called big crunch. The universe will just crunch onto itself. Obviously the gravity has to win, so we don't know what will happen. And there is another possible scenario, that if the dark energy dominates the gravity over time, so the universe will keep expanding forever. And when the universe, so one of the things happening as a consequence is that as the universe expands, so the universe will, from your perspective, the universe will become dark. Why? Because your nearby galaxies are moving away from you, and they will expand, the universe will expand so much that they will reach out of your sight. Remember one thing, when we are talking about the universe, we are talking about the observable universe. We don't really, that was the question I was going to, I will come to the end. What do we mean by observable universe? So there is a universe which might be there, but we cannot observe that, and we will never be able to observe that. So we don't even know that beyond the observable universe, is there a universe or not. Okay, so the second, the big rip. So the big rip is that this dark energy. Okay, first let's call about the big freeze. So if this dark energy keeps going on the current rate, mean it dominates the gravity does not win, the dark energy keep going like this. So let's see this upper figure here. So these lines, so this was the big crunch, right? So that this balloon, it will crunch on itself. So this balloon is universe. Second possibility is these lines, that the universe will become dark, cold, and it will just freeze. But suppose if this dark energy dominates so much, then it will rip apart everything much before we reach the big freeze or even big crunch. That's called big rip. So if what happens is that as the dark energy becomes higher and higher and higher, it's expanding the space itself. Even the atoms cannot exist. Even the atoms will rip apart. So it means that we have no light. Even the light will rip apart. So it means that the universe, there is darkness, eternal darkness in the universe. So that will be the big rip. So yeah, there are these three possible scenarios, starting from the big crunch and then go through the big freeze and then goes through the big rip. So we don't really know, but the current understanding, the current rate is probably the big freeze. So the current understanding is that if at this rate the dark energy keep going, the universe will become dark, cold, and freeze, but it will not rip apart. Okay, so the last question is, how big is the universe? Is the universe infinite? So as I told you that when we talk about the universe, we talk about observable universe. So what do we mean observable universe? So we know that that the light moves with the speed of light, and we know that the universe is accelerating, expanding with some velocity, and this velocity is increasing as we go far and far and far. So what happens is that at some very large or distance away from the Milky Way, the speed of expansion becomes higher than the speed of light. So the light emitted from those galaxies, it will never reach the Earth, because the space itself is expanding at the speed of light moving away from the Earth. So the light will never reach Earth. We will not be able to see those galaxies. So what we know of universe is just observable universe. So this question is very mysterious, that is the universe infinite? Is there something beyond what we can see? And if there is something, is there an edge? Is there a limit? Or the universe is infinite? I think this is a very big question. In many aspects, it's a scientific question. It might has ethical implications in the realm of religion and philosophy. But at least the science probably will never have an answer for this question. Okay, so this was today's topic, and the topic was the Big Bang and the fate of the universe. So hopefully in the next lecture we will discuss some other interesting topic. So in this video, I try to give an overview of the universe as a whole, its beginning and its end, but what's happening inside the universe to the individual objects like stars and galaxies. There are so many interesting things happening in the universe that would define what will happen in the future. So yeah, so we will discuss those in the next slide. Thank you for keeping up with me. See you again. See you. Bye bye.